This is section 4.14.2. Section 14.2 covers infrared spectroscopy. And infrared spectroscopy is neat because we can use a simple principle of chemistry and physics to characterize molecules based on their molecular vibrations. And the reason why we can do that is because in general, molecules are residing in their lowest energy state, which means that all the atoms are in their lowest energy conformations, and the molecules are interacting with each other in some way. However, there are higher energy levels of being that a molecule can have, and those are accessible by infrared radiation. And this infrared radiation, if you match it just right, can promote some of the molecules from a low energy state to a high energy state. So you promote them, and then they relax to give off heat. And they do this through molecular vibrations. And a little fun fact is that this is actually the principle of microwave oven cooking. Whenever you microwave something, you are blasting the water molecules inside the food with infrared radiation. They're vibrating. Little video. There we are. So these are the types of water molecule vibrations that you can see, and they're animated so that they're more interesting. Here is the symmetric stretch, the symmetric in-plane stretch, and the symmetric out-of-plane stretch. But water isn't the only molecule that vibrates. In fact, all molecules vibrate, like CO2. It has a symmetric stretch, an asymmetric out-of-plane stretch, and a symmetric in-plane stretch. These are all animated with much more movement than they normally have. That way we can see the types of movement that they are doing. And CH4 also has vibrations too. Basically, if there's a bond, the molecules will vibrate along that bond, either in plane, out of plane, and symmetric or asymmetric. And this is really useful because we can actually determine what types of functional groups are present in molecules using these stretches, because every functional group has a unique stretching pattern based on its unique thermal energy diagram or thermal energy levels. So for instance, it takes a lot more energy to excite a CH bond from the lowest level to the next, but a lot less to excite a CO bond. And we can measure the energy of light absorbed to figure out exactly what types of functional groups we are looking at. So whenever we put our molecule into an infrared spectrometer, what we get out isn't a series of numbers. It's something that looks like this, where the y-axis is percent transmission, percent T, generally from 100 to 0. Percent transmission means if no light is absorbed, you will have 100% transmission of the light. And if all the light is absorbed, you will have 0% transmission of the light. Therefore, if you have a very large stretch going down, this means that there's a very strong absorption because not as much light is getting through the sample. And then you also are measuring the type of light that is absorbed in the frequency or the wave number. And we say that that is in inverse centimeters. Centimeters to the -1 power is also known as the wave number or the frequency. And generally this goes from 4,000 wave number to 400. And IR spectroscopy is typically governed by Hooke's law, which is a physics equation that talks about the force of springs. And the reason why this is important, hopefully that you've put together, is that each of these bonds can be thought of as a spring, where the stronger the bond, the harder it is to pull the spring and displace the atoms at the end of the spring itself. So that was section 14.2.